Okay, continuing with our lesson on trigonometric integrals. Uh, we're dealing with our part 2, and we left off just talking about this box, what to do when you have an odd power of sine or cosine in the integrand. And we were talking about number 1, where you would take, for example, if sine was raised to an odd power, pull off a sine, and then take your even power of sine that's remaining, sine to the m minus 1, use your Pythagorean trig identity, sine squared is 1 minus cosine squared. Change that and then make a u substitution, laying u equal the cosine of x. You'll see that your integral simplifies greatly. In a similar fashion for number 2, if cosine was raised to an odd power, do the same thing. Take one cosine out. You now have cosine to the n minus 1, which is an even power. Go back to this Pythagorean identity of cosine squared being 1 minus sine squared, and make a substitution that u would equal sine of x. And you'll see good things happening. If m and n are both even, you can use the power reduction formulas, much like we did just in our last example. But let's take a look at example 4 to see this in action. You can see that we do have just one odd power, sine to the third of x. So what we can do very quickly is pull one of those sine factors out, just like so. Then sine squared, of course, has a Pythagorean identity. It's 1 minus the cosine squared of x. And at this point, we're actually very close to being able to make a huge step forward. We're now going to let u equal the cosine of x. If u is equal to the cosine of x, then du would be the opposite of the sine of x, dx. And that would mean, of course, solving for dx, if you'd like, du would be the opposite of the sine of x, du over that. So this integral would become 1 minus u squared times u to the fourth. And then here you have your sine of x, but your dx could be written as du over the negative sine of x. You can see very quickly that these sine of x's are going to cancel out. You'll have a negative 1 out in front. You can factor that out. Simultaneously, you could distribute u to the fourth to both of these terms here. You'd have u to the fourth minus u to the sixth du. And you can see we're so incredibly close to being able to wrap this up. Antiderivative of u to the fourth is u to the fifth over 5. Antiderivative of u to the sixth is u to the seventh over 7. It's a plus a c. Simultaneously distributing a negative and factoring back in that u is equal to the cosine of x, we'd see that we'd get negative cosine to the fifth of x all over 5. A negative times a negative is a plus. We'd have plus cosine of 7, cosine raised to the 7th of x all over 7 plus a constant. And there you go. I do want to point out that if both powers of sine and cosine are odd, if both of them were odd, you'd actually have a choice. You could do the problem from either perspective. And don't be afraid that the answers might look a little different. It's going back to our lesson that we had on differential equations, that you can very often have different solution forms. To wrap up this lesson, let's take a look at forms involving tangent and secant. And let's look at just the very first step here. If tangent is raised to an odd power, and you have tangent raised to that odd power of x times secant to a power of x, what you do is you will pull out not just a tangent, but a secant and a tangent. Pull away one power of tangent and one power of secant simultaneously. Then, of course, you will have tangent to the m minus 1 power, you'll have an even power of tangent, but we have, from tangent squared plus 1 is equal to secant squared. If we were to subtract a 1 from both sides, you'd have tangent squared is secant squared minus 1. Change that remaining even power of tangent into secant squared minus 1, and then let u equal the secant of x. You can already see what we've highlighted here, a secant of x, tangent of x dx. If u is equal to secant of x, your du would be a perfect substitution. So let's see that in action right now. For example 5. How would this work out? Well, like this. We could see that we have an odd power of tangent very quickly. Let's take out 1 power of tangent and 1 power of secant simultaneously and work that through. Then, from what we just saw, tangent squared had a Pythagorean identity of secant squared of x minus 1. So change that even power of tangent using that Pythagorean identity. Then what? Well, very simply, we're going to let u equal secant of x. And when we have that, du would be secant x tangent x dx. So things are looking much better in a hurry. This integral would become u squared minus 1 times u squared, but the secant of x tangent of x dx just becomes a du. We could distribute our u squared in and get u to the 4th minus u squared du. Finishing the problem up, we could take antiderivative to get u to the 5th over 5 minus u to the 3rd over 3 plus a constant. But of course our u was secant of x. So we'd have secant to the 5th of x all over 5 minus secant to the 3rd of x all over 3 plus a constant. And there you have it. This is how to deal with an integral involving tangent and secant where tangent is raised to an odd power. Let's take a look at number 2 on the box. What if you have tangent and secant in your integrand, but secant is raised to an even power? So right now we have secant raised to an even power. What you can do very simply is to factor out secant squared dx. And by doing that, what you're going to see very quickly is that you'll now still have an even power of secant remaining. We took 2 secants away from an even power, but we have this very famous identity. Tangent squared plus 1 is secant squared. So use that Pythagorean identity and then let u equal the tangent of x. The du would be secant squared, and we'd be well on our way. Let's take a look at this in action. For number 6, we have tangent squared of x, but we have secant raised to an even power. So that means pull out a secant squared of x, and we'll leave it as such. Now, we can then say secant squared from a Pythagorean identity. We know that that's really tangent squared plus 1. And the reason why we're doing this, of course, is that because now I have a perfect setup for a u substitution. If we let u equal tangent of x, this integral really is going to get much better in a second. Our du would be secant squared of x dx, which is what we see right here. So this integral becomes u squared times u squared plus 1. The secant squared dx just becomes a du. We can very quickly distribute and get u to the 4th plus u squared du. Taking antiderivatives, we'd get u to the 5th over 5 plus u to the third over 3 plus a constant. But finishing this up, we would have tangent to the fifth of x all over 5 plus tangent to the third of x all over 3 plus c. And that's how to deal with a problem where secant is raised to an even power involving a power of tangent as well. The third part of the box is really saying, what if tangent is raised to an even power and simultaneously secant is odd? There's no standard method to doing that. You might be able to try that by integration by parts. Well, that's it for the lesson. Hope this is going well.